Hi everybody, my name is Isabela. I'm a biologist from the Federal University of Sergipe, which is a Brazilian public institution. This work that I'm going to present for you today is the work that I used for my undergraduate thesis, so to get my degree as a biologist. It's called How Did Large Temporal Changes Affect the Evolution of Tortoises? First of all, the group of turtles and tortoises is called the testudinídeos, which is the order, and basically the main feature that they have is the shell. The shell is formed dorsally by a carapace and ventrally by a plastron. I know all of you know this already. They date from the Triassic, which is around 230 million years ago, and we have around 340 to 350 extant species, which are species that still live, and we have 450 extinct species. Okay, within the order, we have the family Testudinídeos, which is a terrestrial chelonians. It's a highly successful clade dating from the Cretaceous, and we have 58 extant species divided in 16 genera and 140 extinct species. Again, more species that went extinct than we have living ones, and they are distributed all around the globe. This family has lived through great alterations in the globe. We're gonna highlight 4 of them. We have between the Eocene and the Oligocene, around 34 million years ago, there was a temperature drop from around 20 degrees Celsius to 5 degrees Celsius, and a glaciation followed. Then, between the Oligocene and the Miocene, there was a temperature rise with the ice layer receding. That was around 21 to 27 million years ago. Then, in the boundary of the Miocene and the Pliocene, we had from 8 to 5 million years ago, there was a drop in the CO2 concentration, which led to a turnover in the vegetation. And then after that, the temperature came back down due to changes in solar incidence. Okay, that was in the Pleistocene and around 2.5 million years ago. So at least these 4 alterations went through the evolutionary history of the family of terrestrial chelonians. Okay, so we wanted to know how these alterations, and if these alterations actually interfered in the diversification process of this group. For that, we use the Pirate software that takes into account 3 main points, which is the preservation process based on fossilization and sampling, the moments of speciation and extinction, and the speciation and extinction rates. So the idea of the software is what is the probability of this clade, this original clade, having originated the animals that we see today through a birth and death process. Okay, for that we needed a data from the paleobiology database, where we got a list of all the extinct species that we know so far for the group. The catalog of life, we got the list of the extant, the living species that we know so far. We took both the lists and ran through R. That resulted in the graphs that we're gonna see very soon, showing our speciation rates, extinction rates, and our diversification rates. After that, we ran that again in the Pirate continuous that took the previous results that we had, and then made a correlation between those rates with an environmental variable that we chose to be the CO2, and we're gonna see why. So the results that we have was this speciation rate. So this graph here is showing a slight drop from 0.15 to 0.13 in the speciation rate at around 60 to 50 million years, and then we have it basically linear all the way to the end. And then we had the extinction rate that had a very conspicuous rise here at around 6 million years ago, where many species started going extinct. With that, the diversification rate dropped because we had more extinction than we had speciation. Okay, And that actually happened between the Miocene and the Pliocene, which is from 8 to 5 million years ago, around 6 million years ago. Okay, so that is also when we had the drop of the CO2 concentration with a vegetation turnover. Okay, remember after that we ran the correlation coefficient. Okay, so then we got these two histograms, the correlation coefficient for speciation and the one for extinction. Here what we have is that the bars derive from a number of repeated estimates of the correlation between these rates, the speciation and the extinction rates, and the CO2 variation through time. So as shown in both histograms, 0 is on the red bars. That means that out of all the repetitions, 0 was found in a very low frequency, which means that 0 is significantly rare. In other words, as 0 was only found a few times, it is prudent to affirm that there is a correlation because the values found differ significantly from 0. Okay, so we have more estimates that were far from 0 than it is. So if our higher bars were on the red part of the graph, then we would not have a correlation. But this did not happen. So for our discussion, what we have is, we know there was a peak of extinction starting around 6 million years ago. We had a global vegetation turnover that was from C3 plants to C4 plants. This happened worldwide, okay? And that also happened when we had the decrease of atmospheric CO2 levels. This is what we know. This is the fact. These are the facts. So we argue is C3 plants are plants that give us a landscape of closed forest vegetation. So these plants, when we have current levels of CO2 as we have now and mild temperatures, they thrive, okay? In opposition of C4 plants that are adapted to rough environments as savannas, deserts, and arid regions. These are plants that actually thrive when you have high temperature and low concentrations of C2. So what we have is, so what we think happened was, we had low concentrations of CO2, which made in hot areas of the globe, the C4 plants thrived, okay? We based most of our discussion in this paper, which is called Global Vegetation Change Through the Miocene-Pliocene Boundary. And what happened in this work was they studied the fossil teeth enamel of large herbivore mammals, looking for carbon isotopes. So what they found was, they compared actually similar groups of animals before and after the boundary. And what they found was that there were dietary change that happened. So we had previously, we had animals that were feeding on C3 plants that gave place to animals that were actually feeding on C4 plants, okay? So herbivores transitioned from being woodland to being open habitat adapted, mostly in most areas of the globe. That's why this was considered a global event, okay? So we had in Asia giraffes and hippopotamids that were emerging, which are open habitat adapted. We have in North America, we had horses and camel-like animals declining abruptly. These are browser animals, not grazers. But in Africa, we had troglodytes that actually gave way to grazing antelopes. And in South America, taxa adapted to steppes and pampas, which are open habitats, started emerging and diversifying, such as rheas and rodents, okay? All of this happened worldwide except for Europe. Why? Because Europe is a high latitude, low temperature place. So the diminishing concentrations of CO2 need to be in hot areas so the C4 will thrive, okay? So how can this relate to terrestrial chelonians? Actually, we have two survivor genera that we're going to see here. The first one is the testudo. Curiously, the testudo is a genus that happens only in Europe. And this is an animal that we have today, Testudo hermani, that is more inclined to a browsing habit than it is to grazing. So this could help us understand that this was an animal that survived in Europe, and was a browser, so was not feeding basically on grasses, which is basically the C4 plants. So what we think is that if these animals are browsers and survived, they could survive because in Europe the vegetation did not change. So that's why we have a browser, terrestrial herbivore, living still there. Other thing that we know is that there's another survivor genus, the Cynixis genus, which is an African animal. They are omnivores and they survived in Africa. So what we see here is one animal that was a browser, which means they still fed mostly in C3 plants, kept on eating that kind of food, but they were in Europe. That was not a place that was affected by the turnover. What we have in a survivor genus in a place that was affected by the turnover is an omnivore, which means they were not dependent on plant-based food. So the change in the vegetation actually didn't affect as much because they could eat other things. So that's what we think that actually happened. Okay, there was a dietary flexibility in the genus that survived. Okay, the ones that did not have that flexibility actually was substituted by other species. So that's why there was such a high extinction rate, because if they were dependent only on that type of food, they ended up going extinct. So in conclusion, we see that the increase in the extinction rate of testudinídeos beginning around 6 million years ago is consistent with the vegetation turnover between C3 and C4 plants during the Miocene-Pliocene boundary. So what we have is herbivores mostly were affected. Two of the few survivor genera have characteristics that help our hypothesis, which we just discussed, and the living species have dietary flexibility. We cannot, we can kind of assume that maybe the ones that went extinct did not have that flexibility. Okay, so thank you very much. These are my contacts. I hope you found this interesting. And if you have any suggestions, if you disagree on anything, if you agree on anything, please let me know.